Good evening, one and all present here. Myself, Dr. Shivakumar, working as assistant professor in the Department of Mechanical Engineering. For today's session, day 3, session 5, the title is on PEM fuel cells in stationary and transport applications. For this, we have Dr. Balaji Ranganathan to take over the session. So, before that, let me briefly introduce about him. So he is presently working as a senior scientist at Center for Fuel Cell Technology, ARCH, Chennai. He obtained his PhD from CSIR Sikri Karakudi in 2006. He has also worked as a scientist in Southern Petrochemical Industries Corporation SPIC, Science Foundation Tuticorin, and Chennai in the area of hydrogen fuel cells during 2006 and 2008. He did his postdoctoral work in renewable energy, integrated hydrogen energy system at Kitami Institute of Technology, Japan during 2009-10, and later joined at CFCT ARCA in 2010. His research interests include hydrogen energy technologies, electrochemistry, electrochemical process, and energy conversion systems, electrocatalysts, electroplating, corrosion, water, wastewater treatment. Currently, he is focusing in the area of electrolytic hydrogen generation and the PEM-based system, and developed a PEM-based electrolysis system up to 5 kg per day hydrogen production capacity, and working on establishment of automated PEMFC assembly line for fabrication on PEMFC stack, which is first of its kind in India. With over about 2 decades of experience in the area of electrochemical hydrogen generation and PEM fuel cells, he has contributed to transfer 5 technologies to industry in the area of applied electrochemistry. He obtained 5 patents and he published more than 45 papers in journals, conference, and 4 book chapters. He delivered about 75 invited talks in various programs and received outstanding scientists in the area of hydrogen energy technology from Venus International Foundation in 2016. He has also guided about 39 students for their dissertation work, including doctoral and postgraduate students, and serving as a reviewer in various reputed international journals. He executed about rupees 20 crores worth of sponsored project as PI and co-PI obtained from various funding agencies. He is a member of professional societies like Hydrogen Association of India, Electrochemical Society of India, Society of Advancement of Electrochemical Science and Technology. He has also nominated a member in adoption of hydrogen technologies in upstream sector formed by Ministry of Petroleum and Natural Gas, Government of India, and a member of Committee for Development of Capacity Building Programs and certification in line with standards developed for hydrogen subject area formed by Pro Vice Chancellor, Indian Maritime University, Central University Government of India on April 24. He is also an industry technology advisory board member at Green Hydrogen and Hydrocarbon Tech Consortium at IIT Madras, Chennai. He is an executive committee member at Center for Energy Storage Technologies, Nana University, Chennai, and COE in Automotive Technology, at MIT, Nana University, Chennai. And his biographical profile selected and included in 32nd edition of Marcus Suizu in Worlds 2015. So I welcome Dr. Balaji Ranganathan to handle the session.
Very good evening to one and all. Thanks for the introduction and thanks for the invitation to share one session on this particular topic. So I really thank the organizer as well as Professor Jay Kumar for inviting me on this FTP program. So I think one of my colleague Dr. Rahman might have handled one session yesterday. I think my session would be the kind of continuations of above fuel cell activities, what we are working and how the world is looking on fuel cell and for various, especially for stationary as well as transport applications. Just I will share my screen just to check whether it is be visible by everyone. Yeah. So the today topic which I plan to discuss on PM fuel cell application, especially for stationary and the transport applications. Uh, so before getting into the research topic, basically this ARCA is kind of a autonomous body. It comes under Department of Science and Technology. So we headquartered at Hyderabad. Basically, it's a metallurgical research institutions. We have about 11 center of excellence in various aspects of the materials and metallurgy. So all of the centers are placed at Hyderabad. There are two centers which are working in Chennai. That is Center for Automotive Energy Technology as well as Center for Fuel Cell Technology. So we are placed at IIT Research Park. So for the past 15 years. So the main motto of ARCA is that it's not only a pure research and development institutions. So basically, we need to cater the need of the industries as well as the technological development and whatever the research activities which we are currently working on. So it has to be scaled up to pilot plant scale so that the industry people can easily adopt the technology for the commercial aspect. So that is the gap which is normally existing between the academic and R&D institutions. So here say we try to reduce the gap between the academia and industry by working in high TRL level so that we can transfer the technology to the industry. So that is our main mandate. And so far we have about transferred about 16 technology to the 28 industries in India. And so coming to our Center for Fuel Cell Technology is one of the Center of Excellence of ARCA. Basically, we are focusing on low temperature polymer membrane-based fuel cell for stationary as mobility applications, and also another vertical of area which we are working is hydrogen generation through the PEM-based system actually. So that is a major activity of our center. Apart from that, as a kind of spin-off technology, we also working on hydrogen storage material, development of hydrogen storage material and metal layer battery. So these are the major kind of R&D activities which are taking place at our center. And apart from that, actually, we also have a students internship as well as PhD research scholars. We take up every year depending on the project requirement, and they can we will support them for 5 years with a full stipend, and they can register the PhD at any of the NITs and IITs in India. So we have MOU with almost all the NITs and IITs in India, so that they can register the PhD as a kind of external candidate, and they can work with us. And at the end of the 5th year, they may have a degree from the IITs and NITs. So that kind of working model is also available, and many of the PhD students which they have obtained a PhD from our institution. So coming to the aspects of hydrogen, basically the hydrogen is the talk of the day all over the world, especially in India. So to achieve the net zero solution actually. So the solution to obtain the net zero target is that we need to go back in the periodic table towards zero. So if you see then right now we are dealing with more carbon systems, and slightly we are away from that using some electric vehicles and battery-based systems for energy storage application. But even if you want to achieve the zero, the next number is the one, that is hydrogen, which are close to zero. So, and also when you generate hydrogen from the renewable sources like from solar or wind, and get the electrolysis, and that is called green hydrogen, and use it in a fuel cell, you will get back the same water and power. Whatever the power and water which is input for the electrolysis, in the fuel cell, the water and power is the output actually, when hydrogen and air as the input. So it's the exactly reverse of the green hydrogen electrolysis process. So in that context, there is no carbon footprint. So it is almost zero carbon footprint. So that's why people are trying to move towards the hydrogen revolutions and achieve the net zero target actually. So this is some of the numbers of our center's achievements. Basically, we have about 20 years of experience in this area, and As I said, we have trained many technical staff and project students as well as PhD, 100 plus manpower, which we have trained, and we obtained very good numbers of patents in the area of process development, material development towards the and component development towards the development of technology of PM fuel cell. And recently, we transferred two technology to the industries as a component of fuel cell. And not only development of fuel cell, we also do the field trials and the demonstration program almost all over the India. So we have demonstrated up to 8 stationary applications and 2 transport application. And in fuel cell, you might have heard about yesterday, the core component is membrane electrode assembly, which is the core component for fuel cell. And we have a very good infrastructure on developing this core component, and we developed more than 300,000 MVA, through which we can able to generate power of 0.2 megawatt power, and which has been tested for more than 8,500 hours, which is a unique number. Because if you want to develop a technology, then ultimately we need to check the reliability and durability, endurance studies of the system which we develop. So we won't compromise on that particular aspects, and we do rigorous testing of our developed system. And as I said, we produce 10 plus PhD. This center has produced on various aspects of the hydrogen, especially fuel cell and the electrolyzer. And we developed many know-how process actually, because it's when you develop a system, there are multiple components development, which also includes. So each component is a kind of technological development, and it has a very good market value also. And it has about 17 process know-how which we develop, and obviously the patents and publications are quite number. And we executed more than 90 crores worth of projects through it. I mean, in our journey over the past 20 years actually. So when we talk about the hydrogen energy, the transition will not happen overnight. Actually, basically, it's we can categorize the energy transition in 3 different scenario. That is present, intermediate, and ultimate scenario. So right now we deal with a fossil fuel based system like petrol, diesel, and natural gas. All those things which are not carbon free. I mean, carbon. It's also emit greenhouse gases. But it's a kind of intermediate stage. We can look at as electric and hybrid vehicles and synthetic fuel based vehicles, which can also generate power for stationary application. But the ultimate objective of the entire world is that to working towards the hydrogen actually, which will have a almost zero footprint when you use it in any kind of applications. So that is the drive for the hydrogen energy-based energy-based economy. But this transition won't happen overnight. So, but all these energies are being stored through the chemical reaction, which is involved in the material aspects. So, why do you want to go as a hydrogen as an energy storage medium when compared with other supercapacitors or lithium battery when we have a alternative energy storage medium? So, the main advantage is the energy density, which is high than supercapacitor as well as lithium battery. And when you see the cycle efficiency, which is slightly lower than the supercapacitor lithium battery, I will talk about in detail in my subsequent slides why the cycle efficiency for the fuel cell is a little bit low when compared with other. And in terms of discharge rate and life and cycle life, which are quite good number on par with the supercapacitor and lithium battery. So that is a drive for people looking towards this hydrogen-based economy. And when you talk about the hydrogen-based economy, so there are 3 important steps which we need to consider. So the fuel cell will come up with the utilization aspects. But before that, there are 2 important steps. That is production and storage. Actually, these are the 2 important steps which we need to overcome if you want to use it in fuel cell as a hydrogen fuel. So when you talk about the productions, it is not existing asset. So it has to be generated from the electrolysis of water or some hydrocarbon. So the hydrogen is exist in the form of water or hydrocarbon. So you have to get the hydrogen from these 2 sources. So depending upon the feedstock and the method of recovering the hydrogen is being categorized in various types. And right now, the hydrogen is not new for the chemical industry, which are widely used as a reducing agent. And but only thing is, when you want to use as a kind of fuel, the demand is huge, and how you are going to handle the hydrogen when you use as a fuel, especially for the stationary application as well as long storage actually. So that is the one thing as a kind of storage is also equally critical in the case of hydrogen because so these are the various hydrogen production steps based on the feedstock actually. So fossil fuel, if you use as a kind of feedstock, especially natural gas and coal, we will end up with a reformation process and gasification process, and we will yield hydrogen along with the carbon dioxide. So when you want to store this carbon emission, then we have to adopt carbon capture and storage system. And if you use nuclear energy as a kind of input energy for getting the hydrogen from water, so there are two processes, that is thermochemical water splitting and high temperature electrolysis. So these are the two steps which are available, and this technology is not highly matured because of some limitations. That's why people are trying to use renewable energy as a source of electrical energy input for splitting of water molecules. And if you use that electrolysis process, the efficiency is also fairly good and compared with the existing reformation process, and we can get the pure hydrogen. So that's why this hydrogen is colorless, but depending on the type of method which you adopted and the emission of CO2, it is being widely categorized as brown, gray, blue, and green, depending on the carbon dioxide emission while you are generating hydrogen. So in the case of brown, it is quite high, and in the case of gray, it is a little bit lower because we use natural gas, which is having less carbon, one carbon system. So obviously, it will end up with low CO2 emission. When you adapt some kind of carbon capture and storage mechanism, so it turns as a blue actually. So finally, when you do the electrolysis of water using renewable energy, we will end up with hydrogen and oxygen. There is no carbon footprint, and it is zero carbon. That's why this green hydrogen is being considered as a viable alternative source for getting hydrogen without upsetting the environment and zero carbon footprint. So these are the major colors of hydrogen is being classified depending on the feedstock and the energy input, type of energy input which we are using. So the second important step, as we discussed, is the kind of storage actually, because hydrogen is a very, very lighter gas. So it has to be, if you want to store it, to occupies more volume in the cylinders. So, but say for example, if you want to have a passenger car and it has to be run through fuel cell, and you need to carry about 5 to 6 kg of hydrogen in the cylinder actually. So the commercial cylinder which are existing in the market is basically low pressure cylinders where the hydrogen is being stored at 150 bar, and the cylinder water capacity in terms of volume, it's close to 45 to 48 liters, and you can get about half a kg of hydrogen in one cylinder actually. So if you want to have 6 kg or 7 kg of hydrogen on board, you need to carry about 12 to 13 cylinders in the on board actually that are metal hydride, that are metal based, steel based cylinders. So that will also give the payload which is high, and it will reflect in terms of handling the cylinders and total payload of the vehicle. So because of this low volume, higher volume occupation, the hydrogen has to be stored in a compressed manner. So that's why the hydrogen has to be stored at elevated pressure actually, not at 150 bar. Maybe 300 or 700 bar is being recommended if you want to handle huge amount of hydrogen, especially for the transport application. So, but the compression of hydrogen at elevated pressure is also tricky because the compressed gas, when you store it in a sealed cylinders more than 150 bar, the hydrogen has the tendency to form a embrittlement actually, because in the metal cylinders, when you store hydrogen at elevated pressure, obviously the metal embrittlement will happen that leads to explosion of the cylinders actually. So it is not recommended to store hydrogen more than 150 bar under steel cylinder. So we have to see the alternative method of storing hydrogen at elevated pressure in a cylinder. So we have to end up with the composite material, carbon composite material, which are lightweight and it is impermeable to the hydrogen. So the hydrogen embrittlement issue will not be there, and you can store hydrogen at elevated pressure of 300 to 700 bar. So the well-known hydrogen fuel cell vehicle of Toyota Mirai, which they have a carbon composite cylinder where they have stored hydrogen at 700 bar so that they can handle less number of cylinder and high pressure, and the overall vehicle weight will also come down, and mileage can be mileage can be extended as expected actually. So the compressed form of storing hydrogen is one form of storing hydrogen, and another form of storing hydrogen is kind of liquefaction of hydrogen. But that is being used in especially for the niche application because the energy, which is energy intensive process actually. So the amount of energy which you want to spend to liquefy the hydrogen is more than the amount of energy which you are which you want to give for generation. So the liquefaction energy is requirement is more than the amount of energy required for its production. So considering that the liquefaction of hydrogen for a wider application may not be economically viable, so that it is being only used for the niche application. So apart from the gas and liquid, there is another form of storing. It's a kind of solid form of storing hydrogen. It is through metal hydride. There are certain metals which are highly affinity towards hydrogen. There is lanthanum, sodium, and boron-based metal has an affinity towards hydrogen, and it will form a very good physical bonding with a chemical bonding with hydrogen. But when you want to store in hydrogen in the form of metal hydride with this metal, so you have to apply some high pressure and temperature, then only you can able to accommodate this hydrogen in a metal hydride. So apart from the metal hydride, there are some carbon material which are highly porous and high surface area carbon, which is also acting as a very good hydrogen storage material through physics absorption method. And if you see then, so in this case also, the energy requirement for the absorption and desorption should be on par with the near ambient conditions. So that is the major bottlenecks in terms of hydrogen storage. Right now, storing hydrogen at elevated pressure using carbon composite cylinders is being considered as a good option for transportation as well as stationary application in a various sectors actually. So these are the point which we discussed in terms of storage at elevated pressure, and cryogenic temperature is minus 253 degrees Celsius, so that we need to liquefaction is a cost involved component, cost involved steps actually. And in the kind of metal hydrides, as I said, there are few metals which are highly affinity towards hydrogen, and it can store hydrogen up to 6 to 7 weight percentage actually. And as I said, the current technology is storing hydrogen at high pressure using carbon composite cylinders. And there are a lot of R&D program towards development of material and increasing the hydrogen storage capacity much more than the recommended value, so that you can handle more amount of hydrogen within a solid substrate actually. So let us assume these hydrogen productions and the hydrogen storage steps are being parallelly addressed. So we need to have get a power from the hydrogen actually, because the electrolysis is giving power and water as input, getting hydrogen and oxygen as output. Whereas in the case of, if you assume that we address the electrolysis process much economically, and we assume that the hydrogen can be handled in a very good manner, whether it is low pressure or high pressures. So we have to have a device which can perform the converting hydrogen gas into power, that is called fuel cell. And because the hydrogen can be directly converted to power in the IC engine, so that is well demonstrated technology. But why do you want to go through the fuel cell route is kind of energy conversion efficiency from the hydrogen to power is much more high than any of the energy conversion device which is available in the technological. So that's why this fuel cell route is being recommended to convert the hydrogen into power, and the efficiency is quite high when compared with other energy conversion devices. And the reliability and kind of response, these are the two important factors when you want to employ any storage, energy storage device in onboard transport application. So the kind of reliability and the response time for the action has to be high. So considering these major parameters, the fuel cell is being considered as the best choice for conversion of hydrogen into power. So when you talk about the hydrogen fuel cells, so basically it's an electrochemical system. You need to have a positive and negative electrode, and you must have an electrolyte actually. So any electrochemical system can operate at a different temperature range actually. So in the case of fuel cell also it is same. So depending upon the type of electrolyte which we employed for the conduction of proton or anion, so these fuels and the operation of temperature range, it is being categorized as low temperature, that is solid oxide fuel cell, and molten carbonate and phosphoric and direct methanol fuel cell. So depending upon the operating temperature, this polymer membrane-based fuel cell is being considered as the preferable choice in terms of both for stationary as well as transport application. Because you cannot employ the high temperature of SO solid oxide fuel cell in the onboard condition because it need to handle about 1000 degrees Celsius. So which is very difficult for the transport application. So it is meant only for the stationary application. So considering this low temperature operation, this polymer membrane fuel cell is being considered as a viable tool in terms of both stationary as well as transport application. So why when compared with the other type of fuel cell, the PEM fuel cell is getting importance because of fast startup time. As soon as you pass the hydrogen gas in the anode compartment, air from the cathode compartment, immediately you will get a open circuit voltage and it will start to powering the device. And it a kind of fuel flexibility, and you can make very compact fuel cell. Even if you if you want to make a 100 kilowatt system, it won't occupy much space because the anode and cathode interelectrode distance and the type of electrolyte, because here we are not using any liquid electrolyte, we are using solid electrolyte that is called polymer electrolyte membrane or proton exchange membrane, which will take care of the ionic transport between the electrodes, and which are all in few micron thickness. So each cell will produce 1 volt depending upon the voltage and current power requirement. You can configure the cell in parallel or series mode so that you can deliver the required power. So these are very compact, and you can multiple the number of cells so that required power can be met out actually. So it is scalable and the compact, and it is that's why it is ideal both for stationary as well as transport application. So there are major important components which you might have heard from our earlier colleague Rahman. Yesterday he might have briefed about the importance of various components in the fuel cell assembly, like a carbon substrate, which is acting as a substrate material for catalyst loading. The electrocatalyst is basically a platinum based catalyst, which are supported on the carbon, and so when you want to make a membrane along with the electrode, that is membrane electrode assembly is the core component for the fuel cell, where we have shown in this graph, I mean in this picture. And next component, important component, is a kind of flow field plate, which will act as a current collector, as well as it will also facilitate the reactant of hydrogen and oxygen to the respective electrodes. So these are the major system stack as well as system component when you want to make a device of PM fuel cell. So as I said, when you talk about the system, so obviously we should end up with the reliability and how it is being functioning. So the function of the fuel cell depends on each component actually. It's not only a single component, it's a membrane that is act as an electrolyte, and the electrodes, I mean this catalyst, precious metal catalyst has been coated on the carbon substrate, and it has to also allow the various gas in terms of hydrogen as well as air in the respective electrodes. And if you see the thickness of each layer, it's in micron range, so ranging from 220 micron to 500 micron. So these are very crucial when you want to make a device. We need to concentrate on each component development so that you can able to achieve the required power actually. And this each component, the function of each component is different actually. So and the response for each phenomena, especially when you moment, if you pass hydrogen and air into the stack actually, so there's a kind of delay in milliseconds for obtaining the open circuit voltage, because of the some electrical double layer has to be formed in between the membrane and the electrode, and as kind of gas diffusion has to be taking place, because the carbon substrate has to be porous. That's why then only it can easily facilitate the transport of gas molecules from external environment to the electrocatalyst surface. So, and as I said, apart from the power production, the water production is also one of the byproduct in the fuel cell. So you need to effectively handle the water. Otherwise, if you are not effectively evacuate the water from the system, it will create the flooding actually, and which will slowly degrade the fuel cell performance. So all these phenomena will happen from milliseconds to microseconds and seconds, and even in terms of months and days actually. So if you want to ascertain the durability of the PMFC, so there are multiple parameters and multiple component function has to be addressed. Then only you can able to arrive at conclusions of the durability of the PMFC stack actually. So as I said, the water is also being produced as a kind of byproduct apart from the power generation. So in the case of polymer membrane, this membrane will act as a electrolyte as well as the separator actually. Because the hydrogen and oxygen or air should not combine directly. It will create as a kind of the burning actually. Direct burning should not happen. So it should happen in a controlled manner. So and it should not mix with each other. So this membrane will act as a gas separators which are being handled in different compartment, and it also act as a proton exchange between one anode compartment to cathode compartment. This is a kind of electrolyte actually, which will take care of the ionic movement between the electrodes. So when the proton conduction will be effective, it is effective only when the membrane is fully hydrated actually. So the membrane has to be always in the wet condition so that the effective proton transport will take place between anode and cathode. So, but at the same time, if you are not if you allow more water retention within the system, it will create the flooding in the entire system actually. So you must have a effective water management within the fuel cell stack actually, or otherwise it will degrade the fuel cell performance. So water has to be there, but at the same time, it should not exceed the limit. You have to constantly remove the water which are producing at the cathode compartment. So effective water management is one of the key steps which we want to consider while developing a fuel cell stack actually. Apart from the water management, there is another aspects of thermal management because when you say the conversion efficiency of hydrogen to electricity is about 40% and hydrogen to thermal is about 40%. So the overall conversion efficiency is 80%, but 40% goes to in terms of electrical energy and 40% goes to thermal energy. But this thermal energy is a kind of low grade heat because we are operating much lower than the 100 degrees Celsius. So it would be around 50 to 70 degrees Celsius. So it's a low grade heat actually, so which cannot be used apart from the room heating purpose. So, but at the same time, if you are not effectively handle the thermal, if you are not effectively remove the heat from the system, then obviously the membrane will get dehydrated. If the membrane, if it gets dehydrated, then the proton transport will not occur. The performance loss will be seen. So the effective thermal management, that is cooling, whether it is air cooled system or it's a water cooled system, which are being widely used as a coolant for the PMFC system. So the thermal management is also crucial when you want to develop a fuel cell stack. So if you want to make 1 kilowatt fuel cell stack, it will also generate 1 kilowatt heat. So you must have whether it's a open loop system or closed loop system. So depending upon the application, we have to choose water or air as the coolant, and you must have a proper cooling loop so that the effective heat will be removed from the fuel cell stack. And as I said, when you want to ascertain the performance and durability of the fuel cell stack, there are various phenomena which is taking place. That is called flooding, which we discussed. Because when you are not removing the water effectively, then obviously it creates a flooding and the fuel starvation. Because when you draw more load from the fuel cell, obviously the hydrogen and air consumption at the interface will be more. So the rate of consumption of air should be replenished with the rate of should be effectively replenished. Otherwise, the fuel starvation will occur. If the fuel starvation occurs, then there is a lot of fluctuation in the voltage that reflect in the performance deteriorations. And at the time, when if you don't give enough amount of fuel supply, then the fuel, because of the fuel starvation, the cell will act as a reverse directions. So it will act as a kind of electrolyzer. It start to giving positive will become negative, negative will become positive. The kind of cell reversal will happen. So that also contribute the fuel cell loss in performance. And over a period of time, this because we are using very nanocarbon or nanoplatinum as an electrocatalyst. So over a period of time, if it's as because of the fuel starvation and cell reversal and the flooding, this nanoparticle will get agglomerated and become bulk particle, and that also lead to a loss in performance. So these are the various phenomena which will contribute the performance loss of fuel cell PMFC stack. So we need to take care of all the four aspects so that we can operate the fuel cell stack effectively for a longer duration. So as I said, fuel cell will produce a DC power. Obviously, when you want to make any application-oriented thing, so it has to be converted into AC. So the developing the power conditioner. So because whether it is a DC-DC converters or DC-AC inverters, which is also crucially important actually. So because we may think that the inverters and converter which are available for the battery can be directly used for fuel cell, but the case is not same actually, because in the case of battery that is also producing DC power, whereas in the case of fuel cell that is also producing DC power. But in the case of battery, the battery is meant for low current and high voltage operation actually, whereas in the case of fuel cell it's meant for, it's being operated at low voltage and high current. So the entire power electronics is different when you want to make a power converter device for the fuel cell from the battery. So the power electronics is entirely different when you want to develop a power conditioner for fuel cell in order to convert or in order to get a stable voltage from the fuel cell. Because the open circuit voltage of fuel cell is close to 1 volt. Moment if you draw the load, actually it is the voltage will drop down to 0.5 to or 0.6. So this 1 volt to 0.6 per cell, this transition will happen in a milliseconds or microseconds actually. So when you have 100 cells in series, okay, so consider this 100 voltage is an open circuit voltage, and if you draw load suddenly, and if you want to operate the fuel cell at 0.6 volt per cell, the overall stack voltage will become 60. So the voltage transition from 100 to 60 will happen in microsecond and milliseconds duration. So with the wide voltage gap actually and the high current output actually. So the power electronics response to this kind of transition load and transition voltage has to be taken care, or otherwise it will damage the fuel cell performance actually. So the developing a power converter device is very, very crucial and very, very tricky for the fuel cell when you want to make any kind of application oriented. And as also the control and monitoring system, because that is also equally important like power conditioner, because you cannot develop a control logic based on voltage driven process, because in fuel cell all the phenomena like flooding, water production and power generation depends on the current which you are drawing. So when you want to develop a control and monitoring system for the fuel cell, you must take care of the control system through current driven process actually. So it not when you want to develop a control and monitoring system for ascertain the life of fuel cell, so all the logical control has to be driven by the current, not driven by the voltage actually. So these are the main criteria, and when you want to develop a PMFC system, not only a stack, apart from the fuel cell stack, the fuel processor, that means getting hydrogen from the source, and the power conditioner, what we discussed, whether we want to DC or AC, developing a power conditioner, as well as the control and monitoring system, which all together form a PM fuel cell system actually for any stationary transport application. So considering that when you develop all kind of system, so this is the typical flow chart on developing a PM fuel cell testing system. So if you want to test the fuel cell, so these are the basic requirement of a component like a mass flow controller, so which will take care of the controlled flow of fuel as well as air to the stack. and it's a kind of humidification, because as I said, the membrane has to be always hydrated. So in order to make membrane always hydrated, the hydrogen, dry hydrogen, if you pass to the fuel cell, so that also will contribute to performance deterioration. So it is better to have pre-humidify the hydrogen gas. So you have to have a controlled humidification temperature for the hydrogen to be humidified, and the humidified hydrogen has to be passed through the fuel cell. So the humidifier and mass flow controller and the load, actually, whether it is a DC load or AC load, has to be on place so that the fuel cell testing can be performed without any difficulties. And as I said, you are handling hydrogen and air in two different compartments. Obviously, we have to ensure the leak test, actually, because when you pass hydrogen in the anode compartment, it should not come out in the cathode compartment. So we have to ensure the leak, actually, so of the entire PMFC system. The same case for the air also. So if you pass at the air at the cathode side, it should not come out at the anode side. So the kind of leak testing performance has to be done before it has to be tested, it has to be used in the field, actually. So, so what are the parameters, mandatory parameters for testing fuel cell before it is getting deployed? So the mandatory parameters in terms of cell parameters, this how much amount of catalyst which are loaded on the electrode, and a type of membrane, what is the thickness of the membrane, and what is the ionic conductivity of the membrane, which are all has to be known, and the kind of what kind of load which you are using, whether it's inductive load or resistive load which you are going to use. So the type of load which you are going to employ or which you are going to integrate with the fuel cell is also key cell parameters we must be aware of before testing. And the flow field, actually, and the gas diffusion layer, because the gas diffusion layer is a carbon substrate which must have some reasonable porosity so that it will facilitate the gas molecules, and that flow field pattern. So that is also because when you assemble more than 100 cell or 150 cells, the flow distribution of hydrogen as well as air has to be uniform to the entire area. So there should not be any velocity drop or pressure drop or flow. So that has to be ensured. So that can be ensured by proper flow field design. There are various CFD analysis is being performed on optimizing the required flow channel, which will facilitate the hydrogen and air in the fuel cell. So these are the key cell parameters in terms of cell. And in terms of operating parameters, as I said, what is the operating voltage? The open circuit voltage is 1, whether you are going to operate at 0.9 volt or 0.7 volt. So that determines the efficiency of the fuel cell. So say, for example, if you operate at 1 volt, so it is the efficiency almost 100, whatever the OCP which you are done. And if you can able to draw at a constant load of 1, and if you can able to draw a constant current, so the efficiency is close to 100%. That is not practically possible. So it is better to operate each fuel cell at 0.6 volts. So the efficiency close to 55 to 60%, and it is, and the effective heat management, because it is also being considered. So it is better to operate at less more than 0.6 volt per cell, and the cell voltage and cell current is temperature, and how fuel utilization. Because say, for example, if theoretically 12 liters per minute of hydrogen is required if you want to operate 1 kilowatt fuel cell. So some cases, if there are any velocity distribution problems or pressure distributions, and in terms of flow restriction, so there may be a slight increase in fuel utilization. So the fuel utilization, air, and how long you are going to operate. So these are the very important key parameters in terms of operational aspects. And these are the reactant aspects as well as oxidation. The purity of the hydrogen gas and purity of the air is also we must aware of the parameters, right, of what is the inlet composition, and what is the inlet pressure of the hydrogen, and what is the humidification dew point of the hydrogen, because it has to be humidified. So what is the dew point temperature of the hydrogen gas? So same thing is applicable for the case of air. So all those things are key parameters, which is mandatory parameters, which we must aware, and we must have a set of log book is essential before when you want to test a fuel cell stack, actually. And apart from the fuel and reactant, there is a coolant, because as I said, air or water is the coolant. So the water conductivity should be very, very low. Otherwise, the shunt current will be more because it's circulating through the cells. So obviously, it can carry some kind of current. So the shunt current, to avoid the shunt current, it is better to use very pure hydrogen, very pure water, DM water, and what is the flow rate and the pressure, because if you want to effectively remove the heat from the system, so the effective flow rate has to be ensured, then only we can able to remove the heat which are being produced along with the power. And the conductivity of the water should be very, very minimum, and it should be neutral, because it should not be any acidic or alkaline. If you use some kind of acidic or alkaline based water, then it will start corrosion of carbon material or metal connector which we employed in the fuel cell stack. So these are the very key parameters in terms of coolant aspects apart from the fuel and reactant aspects actually. So far, so these are the overall view of how to handle the fuel cell stacks and how to test the fuel cell and what are the important components and importance of the role of each components and how we can ascertain the fuel cell performance. So this is the major activities, as I said earlier, of our center, and this is our pathway adoption, technology pathway adoption. We also do research on development of materials and components apart from the commercially existing material and components for the fuel cell. So, but that will happen at low tier level because we cannot build a high kilowatt stack with a material which we are developing because it requires huge numbers. So it is better. So if you want to develop a fuel cell stack in higher capacity, we will start with a commercially available material, and we will make our own component like gas diffusion layer, membrane electrode assembly, and subsequent cells arrangements and stack fabrication. All those things will happen with a commercial material. That is one of the pathway. And the next pathway, as I said, some material which you are developing, which are alternative to the commercial material. So if it performs in higher, or if its performance is good or on par with the commercial material in a smaller scale, then we will think about the scaling up of the material which we develop. So this is a two-way mechanism for adoption of technology. Once if we develop a full stack, as I said, fuel cell require other BOP components, balance of system. So we also do concentrating on developing air supply system, hydrogen supply system, and coolant supply system, power management system. So all BOP component also we do concentrating and developing a required and customized BOP system for the entire PMFC stack development. Once if the systems are being BOP is being integrated with the fuel cell, so then we will employ the entire system as a product, and we will do field trials to in order to validate the developed system. So this is our pathway adoption for the technology, and so with the pathway which we adopted, we could able to develop stacks ranging from 1 kilowatt to 20 kilowatt capacity over the entire period. And these are the some of the stacks which we develop in our centers, and its performance actually also I been highlighted here. And these stacks are meant for the stationary application because the stationary application and the constraint, the volume and weight of the stack is not a big constraint. So the system which is shown here is shown here is developed a 5 to 7 kilowatt capacity. Actually, it can produce peak power at 7 kilowatt, but we are operating at 5 kilowatt system, which is having all the BOP components. So it's a kind of complete system. So it's a completely grid independent because we have a small battery within the system, which will take care of the initial power requirement for all the controls and valves actually. So it's completely grid independent. So you can, if you have a hydrogen cylinders, then you can get the power of 5 to 7 kilowatt capacity. And these are the performance. And as I said, once if you develop a stack, wherever the hydrogen is available, we will perform our field trials actually. So we performed our field trials in terms of Navy Lignite Corporation and Gas Authority of India Limited, where they have a hydrogen as a fuel. So they are using hydrogen as a coolant in power plant. In the same case of GAIL also. So excess hydrogen if they have, then they want to power the premises through fuel cell. So we had a collaboration with them, and we put our PMFC stack there and deliver the power of 5 to 7 kilowatt, and it has been widely tested, and we could able to power the premises through hydrogen fuel cell actually. So apart from that, GAIL and NLC, we also did a demonstration with the Baba Atomic Research Centers where they have the hydrogen, and we also develop a system for them, and we do demonstration for the stationary application. Apart from the kind of stationary applications, we thought of using these fuel cell system as kind of disaster management actually. So as a part of that, what we did is we carry hydrogen cylinders in a truck along with the PMF systems, and wherever the power requirement and if the grid is power is not available, so through the hydrogen cylinders, actually we fuel the our PMFC stack, and we could able to demonstrate 5 to 7 kilowatt or 10 kilowatt capacity wherever the power grid power is completely absent. So we also demonstrated for the Tamil Nadu government when Radhakrishnan was a chief of the disaster management. So we did a demonstration of the hydrogen truck, which is having hydrogen cylinders and the entire PMF system to power some of their premises actually. So these are a kind of a stationary application which we carried out, and apart from the stationary, and we also did a demonstration for vehicles. It's not a fully fuel cell powered vehicles. It's a kind of range extender. We have a small battery. So with the fuel cell, range can be extended, which was demonstrated for the Reva car as well as fuel cell powered scooters. We have a small hydrogen canisters in the onboard, so that we can meet out the range which we want. And apart from that small Reva car and scooty, we also did a demonstration for the transport application, especially for the Mahindra Bijli, which is having 3 kilowatt and 5 kilowatt system. You can find commercial hydrogen cylinders here next to the driver's seat, and it carry 150 bar, because that time we cannot able to have a composite cylinders which will handle 700 bar pressure, and even Indian government is not giving license to handle hydrogen cylinders more than 200 bar even now. So we did a kind of demonstration. We carry the commercial hydrogen cylinders on the onboard, and with our fuel cell and the entire cooling management system, we could able to run these vehicles in near the IIT campus actually. So with this experience of developing a fuel cell stack and other BOP components, and it is being tested for the stationary and transport application, what we currently performing is that making component, stack is a huge steps actually. About more than 45 steps are involved when you want to make a material to PMFC stack. So earlier we try to make this component and stack assembly. About 30% steps are automated, 70% are we did manually. So we thought that if you want to make a technology commercially available, so the technology adapter must realize how we can able to scale up the technology development, how to fabricate the PMFC component in a faster manner. So with that objective, what we started to establish a complete automation line for developing a fuel cell component as well as fuel cell stack assembly. So this is one of the made an attempt in this country, and we successfully able to develop a PMFC fuel cell stack fabrication pilot line in our premises actually. So you can find various processing equipments, and all the processing parameters has been controlled through SCADA, and it is completely automation system, and each component is being precisely fabricated so that the accuracy and the endurance of the fuel cells can be extended actually. And right now, apart from establishing the PMFC automation line, we do try to demonstrate the fuel cell application for the real application. And one of the objectives that now the telecom tower is being powered through diesel genset when the grid power is not available, and there is a government mandate they need to use their own power for the telecom tower. So because of this influence actually, now we try to put our fuel cell stack as a kind of backup power for telecom tower application actually. So, and we also try to find out the source for hydrogen, because we have a hydrogen electrolyzers. So we try to electrolyze and produce hydrogen on site and use it in fuel cell and powering the telecom tower. It ranges from 3 to 5 kilowatt. So it's a kind of a complete hydrogen supply chain where you can get the power from the renewables and get the electrolysis process, get the hydrogen, do the electrolysis process and get the hydrogen, and store it and use it in fuel cell, and again you will get a power. Whenever the grid power or other power device is getting failure, so the fuel cell will automatically turn on and it will give us a kind of backup power application for the telecom. So that is a major ongoing program which we are engaged in using fuel cell powered telecom tower application. And in the terms of transport application, that is completely hydrogen fuel cell powered vehicles. So there are major component, because apart from the fuel cell, any fuel cell vehicle must have a battery, a small battery, which will take care of the power condition and other power, initial power requirement of the component. So we fuel cell and battery in order to stabilize the power which is coming out the fuel cell, and through inverters it feed to the traction motor, and finally it goes to drive actually. So, and as I said, we need to have a proper coolant mechanism, whether it's a closed loop or mostly closed loop mechanism is required in the case of vehicle application. So you need to have a proper radiator, small and compact radiator. As I said, when you want to employ or when you want to develop a balance of system or balance of plant for the fuel cell, the main criteria is a kind of compatibility. It should be very compact, but at the same time, it should be less power consumption. Say, for example, if you are developing a 1 kilowatt fuel cell, and if you want to power the fuel cell through hydrogen, the BOP power component should be less than 10% of the total power. So identifying a low power consumption air blower and low power consumption radiator and pump is also crucially important when you want to develop a PMFC system, because a low power consumption blower, low power consumption radiator or motor which are not available. So when you want to design an entire PMFC system, say for example 5 kilowatt, if you generate the 500 watt power alone should be used for the parasitic power consumption. So that is one of the major point which we need to keep it in mind when you develop a PMFC system for the stationary or transport application. And there are two kind of configuration which are normally employed in any fuel cell vehicles. One is series hybrid and it's parallel hybrid. In the case of series hybrid, small fuel cell and large battery bank. Whereas in the case of parallel hybrid, it is reverse actually. They have a very good large fuel cell which will take care of the 80% of the power or 90% of the power requirement for the vehicle application, and small battery bank which will take care of the powering the BOP component and other control system. And this Toyota Mirai, which was widely used for the fuel cell, is being configured through this parallel hybrid configuration actually. So as I said, when you want to develop a fuel cell vehicle, so these are the key requirements. One is the response and proper handshaking between each component is one, and the transition response, it should be 10 to 90% power. It should happen within a second actually. So the kind of response and the power conditioner and the other component is also crucially important when you want to develop a fuel cell powered electric vehicles. And these are the key components for the fuel cell electric vehicles. As I said, the hydrogen cylinders, which are hydrogen has to be stored at 700 bar, and the cylinder should be lightweight. It can be made up of carbon composite cylinders, and the nozzle, especially if you want dispensing the hydrogen gas to the fuel cell, so the fuel filler and the nozzle is also equally important, designing the fuel nozzle, because you need to handle the hydrogen. So the CNG nozzles may not be suitable. So you have to reconfigure the nozzle for dispensing hydrogen, and the cooling system, that is effectively how to remove the heat from the fuel cells, and power conditioner as we discussed, DC-DC converter, DC-DC inverters, which are also crucially important when you want to make a fuel cell electric vehicles. And there's a kind of comparison whether when we have a lithium-ion battery vehicles on board, why do you want to go with the fuel cell electric vehicles? So there are key three parameters which we need to consider. That is price, range, and time to refuel. So in these aspects, if you consider that right now the fuel cell hydrogen vehicles are price is high because of low volume of usage actually. So that can be reduced actually when you increase the market and increase the volume. And if you see the range wise, actually, it is we can handle up to 400 to 500 kilometer range actually when you carry about 5 kg or 4 kg of hydrogen using high composite, high pressure cylinders. And the time for refueling the hydrogen is very less. Like a CNG, you can handle refueling the vehicle within 3 to 4 minutes actually. So whereas in the case of electric vehicles, this time to recharge is high and the range anxiety, which are not unavoidable. So because we cannot extend the range anxiety. So and that electric vehicle cost right now is low because of the high volume. And when compared with petrol and diesels, this cost can be considerably bring down when you increase the number of volume and mass, and the range is on par with the fossil fuel based system, and the time to refuel is also on par with the fossil fuel system. And that's why the when compared with battery based electric vehicles, the fuel cell based electric vehicles may gain importance in future. And so though the technology has been demonstrated widely for the commercial applications, there are some challenges in terms of cost, because we are using precious metal catalyst and the membrane, which are also one of the cost component, and the bipolar plate, which will facilitate the gas molecule distribution among the fuel cell electrocatalyst. So all these are very cost component. That's why the DOE has set the target of $40 to $30 per kilowatt. So right now it's about $200 to $250 per kilowatt. So there is a scope for the improvement while developing novel materials. So there may be cost can come down to the thing, and the BOP components are equally important because not only is stack. So when you talk about the system, the development of balance of system like low power hydrogen supply system and low power blower and low power effective DC-DC converter with having high efficiency. So all the BOP components development is also equally important apart from the fuel cell stack actually. And though these fuel cell stack and fuel cell vehicles are ready, we need a required infrastructure. Otherwise, the fuel cell vehicle will not take off. So fuel infrastructure like a petrol pump, must have a hydrogen dispensing station. Right now, we could able to see much more CNG based petrol pump, but like that we need to have a hydrogen filling station widely so that the fuel cell electric vehicle adoption will be much easier. And there is always the debate between the price and cost. Actually, if you want to introduce a new technology for the commercial market, obviously the profit has to be less so that the faster adoption of the new technology will be easier. So we must compromise on price aspects, and considering the cost, we can able to push this new technology for the commercial market. And right now, in India, the fuel cell market is for a telecom tower, what we discussed, because about more than 150 telecom tower, which is being operated by the Geo, is being powered through hydrogen fuel cell, because they have an internal reformer which will take care of the converting methanol or ethanol into hydrogen. So the produced hydrogen is being used in the fuel cell to deliver the power. So that is the current market for the hydrogen fuel cell, especially for the stationary applications. And these are the various fuel cell car developer. Almost all the leading automobile manufacturers, they develop a Hyundai, Toyota, and Honda. So they developed a fuel cell powered hydrogen car, and I could also experience the hydrogen fuel cell vehicles, which is being developed by Toyota Mirai in Canada, where I am visiting. So it's quite good. You can see the 120 kilowatt fuel cell, which is on the front side of the vehicles. So it's about 120 kilowatt Toyota hydrogen fuel cell, which is so compact, and the running time and the range of fuel cells is about more than 500 kilometers. Even our Honorable Minister Nitin Gadkari also using these hydrogen vehicles actually. So it's a kind of faster adoption of and realizing the technology for the commercial market. And apart from the passenger car, the China's and Germany is also demonstrating hydrogen fuel cell powered trains, and India is also on the way to power the hydrogen train, but not through fuel cell. It's like the other IC engine based concept actually. So, but soon we can also expect this hydrogen power train in India also. And there are key challenges as we discussed, the cost and the market penetrations. And if you consider that all the challenges, if it overcomes, so what would be the net energy analysis, whether it's a battery or hydrogen? Because the hydrogen is, if you consider, is being generated from the water. So, and get the power from the renewable, split the water molecule, get hydrogen and oxygen and store it. Whenever you require, use this hydrogen oxygen in fuel cell, get again power and water. So this process is similar to the battery charge and discharge mechanism. So in that case, hydrogen and the battery both are energy storage medium. So which one will be the better? That obviously we will end up with that kind of questions actually. So there is a kind of analysis which is based on energy stored on invested actually. The term which represents the ratio between the amount of energy which you want to make 1 kilowatt battery or 1 kilowatt electrolyzer or fuel cell and amount of energy which you are getting from the device over life period actually. So that term is nothing but energy stored on invest actually. If you see this, RHFC is nothing but hydrogen getting from the water and use it in fuel cell, again you're getting water and power. So that is similar to the battery charging and discharge mechanism. Right now, the energy stored on investment for the RHFC, that is fuel cell base, is higher than the battery, because the amount of energy when you want to develop a 1 kilowatt battery is more than the amount of 1 kilowatt fuel cell which you want to develop actually. So in that context, the energy stored on investment aspect is more for the fuel cell based electric vehicles when compared with lithium battery based electric vehicles. And second aspect is efficiency, because you are using renewable power to store in the form of hydrogen storage or the battery storage. For battery, even if you store 1 kilowatt power in the battery, you can get back 800 to 900 watts from the battery. So over life period time, you can also get it the same power. Whereas in the case of fuel cell and electrolyzer, because the chemical reaction which is involved for the generation of hydrogen from the water is nothing but water and power will give hydrogen and oxygen. So the same reaction, the reverse reaction, hydrogen and oxygen will give power and water. So the chemical reaction is same. Obviously, the power energy input and energy output should be same. That is the theoretical aspects. But the practical case, when you want to generate hydrogen from the water, you have to give 2 volt as an input. When you use this hydrogen in fuel cell, the open circuit voltage should be 2, but it should be 1. So the theoretical voltage is 1.48 volt is required to generate hydrogen from the water. The same 1.48 should be obtained in the fuel cell when you give hydrogen and oxygen in the system. But practical case, the amount of input which you want to give in the electrolysis is 2 volt, and the amount of output which you are getting from the fuel cell is about 1 volt. So the efficiency is close to 50% or 40%. That's why the net efficiency for the fuel cell is 30%. But lot of scopes are there to bring down the voltage window close to the theoretical of 1.48 volt. So you can also reduce the voltage for the generation of hydrogen is close to 1.48. But at the same time, you can also increase the open circuit voltage of fuel cell to close to 1.4. So that the voltage window, if you try to minimize using developing a novel material and novel device, the fuel cell efficiency can also be improved. Even if it is improved, it may not go beyond 50% or 60%, but 80% achievement, though it is not possible electrically, considering the carbon footprint. So the fuel cell electric vehicles will take off the battery-based electric vehicles. So and till then, so there are many attempts are being taken care whether the hydrogen can be used in the IC engine with a small change in the spark plug configuration and use it for power generation. Yes, it can be done, and it has been demonstrated widely. And only the combustion ratio, because the hydrogen gas is lighter, so the combustion volume has to be higher. And the one thing which you want to take care of is the emission of NOx actually. So because the water is though it's the water is a byproduct, when you have a combustion of air and hydrogen, there may be a possibility for the NOx emission, but there are attempts to reduce the NOx emission, and even this Mahindra is recently demonstrated the hydrogen IC engine powered buses actually. So they are still conducting various trials, and so far they have conducted 250 kilometers of hydrogen IC engine powered buses, and they use for trek actually. So long distance trek, because that does not require high speed and it requires some constant speed, and they can want to use it this hydrogen IC engine concept for the long distance trek, and it is on demonstration phase actually. So there are advantage and disadvantage when going with hydrogen powered IC engine and hydrogen powered fuel cell, but the overall efficiency in terms of the fuel cell will be the better than the IC based engine. And apart from that, there is a kind of creation of awareness among the people, too much aware of this hydrogen based, what is hydrogen based things. So in that context, actually, if you see this atomic weight of hydrogen is 1.008, which represents the 8th October, every year is being celebrated as Hydrogen Fuel Cell Day. So in order to create more awareness among the people and among the technology actually, so we also do demonstration, celebrating the Hydrogen Fuel Cell Day for the past 7 years by conducting various workshops and live demonstration. And it can also create a lot of knowledge and awareness about the technology, so that we can realize the hydrogen fuel cell electric vehicles as well as stationary application in very, very near future. So thank you for your attention, and I am open for any kind of discussion and question. Thank you.
Dear participants, I would like any of you to ask queries. Sir, Mr. JVLS is asking about research topics of fuel cell for the research scholars.
Yeah, actually, it's a kind of interdisciplinary field actually. So it is a lot of scope for the improvement and the component development in terms of engineering as well as science aspects. So especially for the engineering aspects, the development of this metallic bipolar plates, because when you want to use this fuel cell for the transport application, the size and weight of the fuel cell has to be minimum actually. So it should not occupy more volume. So earlier people were using graphite based flow channel plate for making fuel cell stack. But the graphite is lightweight, so that you have to use thicker plate, and then only you can able to maintain some kind of mechanical strength. When you use a thicker plate, for example, 4 mm, 3 mm plate, and if you want to have a 100 cells, the plate distance itself is more than 500 mm actually. So, but it occupies more volume actually. So that's why the people are trying to move away from the graphite. When you use a metallic plate like a stainless steel or other titanium, the density is more, but you can use a very thin 0.1 mm or 0.2 mm sheet, where you can make a desired flow channels, flow pattern through some laser machining or laser technology. You can make a very desired flow channel on the 0.1 mm or 0.2 mm sheet. And if you combine these two 0.1 mm sheet, it will act as a bipolar actually. So the development of metallic bipolar based PMX stack is also one of the key area where people can engineering people can look about that. And the protective coating, when you employ a SS based or a titanium based, there may be a possibility from corrosions actually. So it is, you must have some protective layer coating like titanium nitride, iron nitrate, chromium nitrate, that kind of coating aspects also to be considered. So the developing very thin metallic bipolar plate for fuel cell is one of the best area for engineering, especially mechanicals. And in terms of electrical, as I said, the power converters actually, developing a power converters which is not available in the market actually. As I said, because it need to handle low voltage and high current. So the entire power electronics is different from the battery. So in the case of electrical and electronics people, they can address the developing a high efficiency DC-DC converter or inverters for power. And in terms of scientific aspects, as I said, using low noble metal content electrocatalyst and high activity, and developing a membrane alternative membrane to the commercially existing membrane. These are the area where people can concentrate and they can come up with a new methodology and new materials actually.
Sir, excuse me, sir, I'm Perichiappan consultant.
Yeah, please.
I got one question, sir.
Yeah, please.
Very good presentation. First of all, I am thanking for your very good presentation, knowledgeable and very detailed thing you have given, sir.
Thank you.
Sir, regarding this Bloom Energy, already they made a polymer membrane and liquid alkaline as well as solid ceramic material.
Yeah.
They got efficiency around 52, 54 and 37%, sir.
Yeah.
Bloom Energy. In
Yeah.
USA, they are doing it. And of course, they are also only stationary. I don't know whether they are going for transportation or like your fuel cell transportation thing they are doing or not. I don't know.
Okay.
But they are doing in the 2 gigawatts and 5 gigawatts and all. They are doing it in the Microsoft companies and Google and all. They installed their generators that,
Yeah.
of course, this fuel cell.
Exactly.
But
Exactly.
actually,
Yeah.
yours also, your PM also similar to that only. I'm actually that I'm comparing. Both are
Yeah.
mostly similar only.
Yeah. I mean, as you said, so the Bloom Energy majorly working on high temperature fuel cell, that is solid oxide fuel cell actually. So
And high voltage also, high voltage, high current also, sir.
I mean, high voltage and high current in terms of, because when you go with a solid oxide fuel cell based system, because as you said, the reactions are common for PMFC and SOFC, but the limitation is that the solid oxide fuel cell cannot be employed for the transport application, because you need to handle close to 700 to 800 degrees Celsius of temperature, and then only you can able to take the power. So it's meant only for the stationary application. So the Bloom Energy is maximum concentrating on developing a solid oxide fuel cell, especially for the stationary application. Rightly you mentioned for the Microsoft and all those things. But in the case of PMF fuel cell, actually, it's meant both for stationary as well as transport application actually, because of the
alkaline, sir? So solid alkaline.
The alkaline fuel cell is also not highly matured, because there are two reasons. The one is that because the alkali, when you handle alkali, obviously it will end up with a carbonate formation over a period of time. So because the atmospheric carbon dioxide may absorb during over a period of time, it will form carbonate, which will reduce the quantity of alkaline over a period of time. And over a period of time, the performance will also come down. And that is the
erosion will be then, sir. Erosion will be then.
Obviously, we will end up with the erosion. And you need to handle some alkali apart from that actually. So that's why this alkaline and molten carbonate fuel cell is not taking off. So that's why it's going prefer for the PEM-based system for stationary as well as transport. And rightly you said the SOFC is only meant for the stationary applications.
Okay. PM is now suitable for transport.
PM. Yeah, both for transport and stationary also.
Stationary. Oh, okay, sir. Thank you. Very well answered, sir. Thank you, sir. My question answered well, sir. Thank you.
Thank you.
Thank you, sir. Sir, Mr. Dr. Rajkumar P has asked, as discussed, converter component has high current rating used for fuel cell practical implementation. Which type of component in the bracket is GIC or SI based inverter rectifier practically implemented, sir?
Yeah, actually the GIC and SIC based, GIC is majorly preferred actually. So, but right now the kind of ready-made off-shelf product is not available in the market actually. So, as I said, it is better to develop our own kind of components to handle high current at lower voltage actually.
Okay, sir. And Jeevanathan has asked why Indian government gave 150 bar.
Because so now they have extended to up to 300 bar in some areas actually, because of the safety concern actually. So because only the safety, because now only the hydrogen awareness is being slowly created among the people. And second aspect thing, the cylinder availability, because when you want to handle high pressure cylinders, you cannot handle steel based cylinders because of the hydrogen embrittlement. So you need to have a different material, which is carbon composite material. So the entire engineering cylinder design is different, and the material is also not available in India. So this is the two reasons. One is non-availability of the carbon composite cylinders, and second aspect is safety. Because of these two reasons, now the government is slowly stretching this hydrogen operational pressure up to 200 to 300 bar. But hopefully in the future, they may also extend to 700 bar also.
Sir, this is Uma Mageshwari.
Yeah, please, ma'am.
Sir,
Yeah, please,
Yeah,
ma'am.
yes, ma'am.
sir, I just want to know why we need to go for current control for in the case of power conditioner. Sir, usually we used to have a outer voltage and inner current loop.
Because basically this fuel cell, all the phenomena actually basically, if you control the voltage, so it reflect on the load actually. So because if you want to operate some system at a constant load, the voltage fluctuations may not be exactly monitored. So the water formation, heat formation, everything depends on the load actually. It's a current driven process actually. So even at the OCP, there won't be any much formation of water. So it is very, very difficult to monitor the voltage and developing a strategies for voltage driven concept, because all this flooding, water formation, and everything is being controlled by the load actually. The load is nothing but the weight of current which you are drawing. So that's why I said the current driven process is more preferable than the voltage driven process.
Okay, sir. Thank you.
Thank you. Thank you.
Participants, anyone else?
Another question in the chat box: why the fuel cell concept is not yet implemented in India?
That is because of the hydrogen infrastructure availability and the cost actually. These are the two major challenges. But right now, once the hydrogen infrastructure is available, then the fuel cell will also emerge out actually. So only thing is, once the hydrogen fuel is available, then obviously the engine will take off actually.
Another question is: carrying hydrogen fuel tank is safe?
I didn't get it, sir. What is the question, sir?
Carrying hydrogen fuel tank is safe?
Yeah, it's much safer actually. There is a lot of sensor which are widely available in the market. So even the handling hydrogen is much more cheaper than, safer than the LPG, because the flammable limit of hydrogen is only 4 to 75% in the air. So there are plenty of sensor which are available even at the 2% LEL level. If it is assigned, there is a kind of alarming systems are there. So, and it's also very lighter gas actually. Even if it is expelled, it will go off immediately to the atmosphere. So it is much more safer than the handling LPG.
Okay, sir. Sir, myself, do we need things like in case of lithium polymer, we have battery management system, thermal management system.
Yeah.
So do you have anything like that is kind of required for?
Yeah. That's why the power management, the thermal management is also important like battery. But you have some kind of flexibility here actually. So in the case of battery, you need to have an external cooling circuit actually, not within the system actually. So whereas in the case of fuel cell, you can have a coolant channel in between the cells actually. So the effective thermal management is much more easier than the battery based system. So at the same time, the power management system is also because you can operate the system at constant voltage or constant current mode actually. So the power management, this is DC converters and DC inverters is also equally important like battery. Power management system is also important actually.
Okay, sir. And one last thing, sir, do we have any kind of consumable thing which is much significantly costlier apart from the hydrogen?
No, only hydrogen is a consumable because the maintenance is very, very less in the case of fuel cell. Because the cost of the electricity is nothing but cost of the hydrogen. So right now, if you see the cost of the hydrogen in the commercial market, about 1 meter cube is about 77 rupees, 80 rupees. So what we are getting the hydrogen cylinders, so it's about 6 meter cube cylinders. It costs about 700 to 800 rupees. So per meter cube cost is close to 75 to 80 rupees. So if you use 1 meter cube hydrogen in fuel cell, you will get 1 kilowatt power. So obviously the unit cost goes to 70 to 75%. 75 rupees. So the power generation, when the hydrogen cost come down, the power cost also will come down actually. So the hydrogen is a major consumable. If you have a closed loop thermal management system, then you must have some constant volume of water. So that can also be used to very long time actually. So the hydrogen is only the consumable when you want to operate the fuel cell for a long time.
Okay. Anyone else would like to ask questions?
Yeah, Godwin from Crescent Automobile.
Yeah, please.
Yeah, sir, I have a question. I have two questions actually.
Yeah.
I'm from the automobile department. We have few elective subjects related to fuel cell vehicles, hybrid vehicles, and all those.
Okay.
As of now, those subjects are totally the theoretical form. We want to implement few laboratory experiments for the same.
Yeah.
But we cannot right away go with the research scale. So I need your advice on this actually.
Yeah, actually, there are some commercial kits are available for the educational purpose, basically, sir. Even the cost of the you can buy a fuel cell stack, 1 kilowatt fuel cell stack, not more than 3 lakhs actually. So there are few watts fuel cells is also available in the market, and you can do some kind of preliminary studies with that fuel cells, which will not cost much than. I mean, if you buy a 500 watts stack is also available, 250 watts or stack is also available. Only and there are Indian manufactured fuel cell test benches. If you want to test the fuel cell, so the Indian manufactured fuel cell test benches also commercially available. That also not cost much than more than 3 to 4 lakhs actually. So you can build your own lab with a indigenously available test bench and a commercial fuel cell, so that you can do demonstration and you can feel the operation of fuel cell systems. So that way would be the best starting point for the academic purpose.
Yeah, thank you, sir. One more question. Day before yesterday, we had a session on model-based development.
Okay.
So, how far this model-based development and this MATLAB and Simulink models are involved in your research, and how it is helping you out?
Actually, this MATLAB and CFD analysis are very much needed, because these MATLABs are because there are some materials which are commercially available. If you want to combine those material as a common and want to develop a performance of the system, MATLAB is widely being used. In case of CFD, as I said, the flow channel pattern, so it is widely being adopted actually. So it should be less pressure drop and high velocity and the effective transport of the gas molecule within the catalyst. So that kind of studies can be performed through the CFD as well as these things.
Thank you, sir. Thank you so much.
No other questions from the audience, then we can conclude the session, sir. Shivkumar, sir.
Yeah. Anyone else, sir? Okay, I think we have come to the end. So let me, on the behalf of everyone here, I extend my heartfelt gratitude to Dr. Balaji Rangarajan, Senior Scientist at Center for Fuel Cell Technology, ARCF Chennai, for taking time out of his busy schedule to share his invaluable expertise with us on the topic PEM fuel cells in stationary and transport applications. So your insightful presentation has given us a profound understanding of the applications of PEM fuel cells. The knowledge you shared today will undoubtedly inspire and empower us to pursue innovation solutions in this field. Once again, thank you for your time, effort, and dedication. We hope to have more opportunities to learn from you in future, sir.
Thank you. Thank you all for patience listening. Thank you all.